Factors affecting reaction rate, part 1. So with this series we will look at around 5 things that affect the rate of a reaction, and we'll see how it affects the rate of a reaction and try to describe it in terms of collision theory. So the first thing, nature of reactants. The nature of the reactants themselves. How does that affect the reaction rate? So over here I have an old school overhead projector, and hopefully this turns out really well. I'm going to just show you an example of how the nature of the reacting species affect the reaction rate. So in both of these beakers here, these are beakers here on an overhead projector, I have a piece of calcium right there, and when we add that into water, it will actually react with water, producing some hydrogen gas and calcium hydroxide. So the calcium will react with water and make an aqueous solution of calcium hydroxide. In the other one, I don't have it cut yet because it's actually very reactive. I'm going to be using pure sodium. It is actually stored in oil because it is so reactive with water. Even with the sweat on your fingertips, there's a potential it could react with that as well. And of course, when that reacts there, I'll get sodium hydroxide. And I think to balance that out, I need that. Can't really see those equations too well there, but that's okay. I actually pulled this from your textbook, so if you wanted to see the exact reaction, you could definitely look in there. So sodium metal comes in a jar like that. I'm going to put my, of course, the old trusty safety goggles on first. I should have washed them first because I could barely see out of them. So sodium, it's a very, very soft metal. So soft that I could actually just simply cut through it with a knife or a scapula. So I'm just going to do this off to the side. Cut just a little piece. I'll try to get a piece very similar in size to the calcium there. Okay, so it's right here. It's on the tip of these prongs here. So I'm going to try to drop both of them down at the same time, and hopefully you can note what happens. So the sodium one over here, of course, you can see is much more vigorous. In fact, I have a lot of hydrogen gas being produced as a result of that. And the calcium metal, we can kind of see it's reacting. You can see a few bubbles there, but not nearly as vigorous. And yet, very similar reaction here. A metal combining with water, metal combining with water. Okay? So the nature of the substances, where they are in the periodic table, how small they are, how far their valence electrons are from the nucleus, all those are factors that come into play when we're talking about nature of reactants. So when looking at that, some reactants react more readily than others due to the placement on the periodic table and other factors, of course. We have different things happening there with nature of reactants. The next factor, concentration. Concentration is the next one. I also have a demo over here with the old overhead projector here. It's good for something still. So this time with the overhead, I have two different concentrations of hydrochloric acid. Okay. This one here is 1 molar HCl. This one's 2 molar HCl. So we can see, of course, this one's double the concentration. There are double the reacting particles in this one compared to the other one. And in this one, it's a very similar reaction, except it's with magnesium ribbon. We also get the generation of hydrogen gas, but I'll try to keep everything constant here. I'll try to get two identical pieces of magnesium. Just shine them up a little earlier here. Very similar pieces there. This one may be a little bit bigger, but it won't make a huge difference. So if we take a look when we drop them in, and if we look over here, we see that reacting much more vigorously than that one, because I have double the reacting particles on this one. And it's on, and there we go, it's gone. And this one, of course, is still reacting here. You can see that. So the concentration, and this I chose to change the concentration of hydrochloric acid. So if we look at concentration, a couple of things we could mention there. The higher the concentration of the reactants, the larger the rate. And by that, of course, I mean faster. This is due to more particles colliding with each other and increasing the chance of overcoming that activation energy barrier that we talked about in the last video. More will collide with the correct orientation in the right way, just like a puzzle piece, and meet those energy requirements in order to overcome the activation energy barrier. So that's concentration, experimenting with that. The last one I'd like to do for this segment is surface area. Surface area. Let's see here, I did have a thing here, here it is. Cornstarch. I have a bottle of cornstarch here, or not a bottle, a box I guess. So I'm just going to put a little bit on this pad here and see if we can light it. So I'm exposing the flame to the cornstarch that's on there. You can see a little bit of a flame there. Nothing too exciting to write home about though. So if we notice though, the air, the oxygen in the air and the flame is only being exposed to that outside part of that. If there is a way of increasing the amount of surface area that the oxygen and the flame are exposed to, we would get a better reaction. So I'm just going to take over that leftover cornstarch. Maybe grab a little bit more here. And put it on this paper. You need almost 3 hands to do this. I'm going to light this candle. So what I'm going to do is I'm going to try to spread the surface area over the flame. So in other words, make the particles as fine as I can. The cornstarch is pretty fine already, but I can make it finer by simply blowing it over the flame. So we'll see if this makes a difference. Oh darn it. It usually happens. Usually goes out. I end up blowing the cornstarch too low and it shuts the darn flame off. Let's try it one more time here. Okay. Try this again. Oh, there we go. So you can see a really nice bright flame there all of a sudden. So surface area. Increasing the surface area of the reactants increases the rate of the reaction. So as you saw, I increased how much of the reactant was exposed to the flame and to the oxygen. Small surface area, for example, just dumping the cornstarch straight onto there, there's fewer collisions of reactants than if the surface area is larger. So forcibly trying to get as small particles as possible. Another example of that is if you take a look at a sugar cube versus powdered sugar, we would have just the outside of that sugar is being addressed by the water there, slow dissolving, whereas if we take that same sugar cube, grind it up, expose all the particles, faster dissolving in that fashion. So more collisions result in increased chances of reactants overcoming the activation energy barrier. So more collisions, thereby increasing the chances that some of those reactants will have enough energy to overcome the barrier. That's the end of part one. We'll look at the remaining factors in the next part.